Hello wonderful person, this is Anton, and in this video we're going to be once again discussing the very foundation of how we understand the universe itself. And that's because for many decades a lot of cosmologists and scientists in general relied on something referred to as the Lambda CDM model, also known as the concordance model or the lambda cold dark matter model, the standard model of cosmology that tries to explain everything from the Big Bang to the way that galaxies cluster together and eventually evolve various enormous structures. But in the last few years, especially based on some of the most recent observations, some cracks in this model started to appear because some of the things seem to not match and some things don't make as much sense. With all of this becoming even more apparent following this recent study based on a massive survey of 1,600 physicists that basically suggests that there is no actual consensus yet, and we may be witnessing a kind of a shift in how we view space and cosmos itself. And so today we're going to focus on some of the studies in the description and discuss some of the facts and discoveries in them, and discuss what physicists actually believe, and talk about some of the recent tests and recent observations that challenge our assumptions in regards to that perfectly smooth universe we've been studying for many decades. Because these recent studies now suggest that a lot of these assumptions may have been just a little bit too simple. But before we jump into the actual results and discuss some of the math, let's actually talk about the people doing the math, because there was an extremely recent survey conducted by the American Physical Society, and the results from the survey, along with other studies, should be in the description. And even here, there was already a major surprise, something that many physics textbooks don't really tell us much about. And that's because most of the facts we know about from these textbooks in physics don't actually have majority support among scientists, which is quite unexpected. For example, when it comes to the famous Big Bang theory, most people may assume that it means the beginning of time. But 68% of physicists seem to agree that it's not beginning of time, and instead describes the evolution of the universe from a hot, dense state. As a matter of fact, they suggest that the time itself may not even have a starting point, with only 20% describing Big Bang as the start. But even more intriguingly, the most famous cosmological model, Lambda CDM, did not attain majority support either, and mostly because of a problem we usually refer to as the Hubble tension. And this persistent disagreement between how fast we see the universe expanding versus what's calculated is actually one of the main reasons nobody seems to agree on what's causing all of this, with most scientists agreeing on something entirely different. Either this is some kind of a new particle, a result of still unknown quantum gravity effects, or possibly just systematic error in some of the data, which tells us that the frontier of cosmology is very much alive and, quite frankly, is a bit of a mess right now because there seems to be quite a lot of disagreement. With something similar discovered in trying to explain the ideas behind quantum physics, or in trying to explain what happens inside black holes. And some of the biggest disagreements were actually in regards to gravity. Even though it's basically fundamental to our experience on Earth, nobody can even agree what's causing it or how it works, with approximately a third of physicists basically settling for no opinion. As in, they have no idea where to even start, so they chose not to answer. Which basically now brings us to these new studies, and specifically 3 studies, that once again highlight this issue in a little bit more detail. And in this case, these are discoveries based on an idea referred to as FLRW cosmology, also known as Friedmann-Lemaitre-Robinson-Walker cosmology. Essentially a kind of a space metric that provides the main mathematical framework for all of the modern cosmology and tries to describe everything around us. And it's essentially based on 2 main core assumptions. The assumption number 1 being that the universe looks the same at every point no matter where you look. This is referred to as homogeneity, or basically the universe has no center. And it's also isotropic, or it looks the same in every direction, whether you look right, left, up or down. And so, in other words, the universe should have the same density, same laws, same everything, everywhere. Otherwise, things will just not work because a lot of modern formula and a lot of modern cosmology depends on these fundamental principles. And this is essentially something that's been assumed for approximately 100 years now. And because of this assumption, it allowed us to use relatively simple math to describe the universe's expansion and to describe additional observations from very faraway objects. But there's always been a bit of a catch. The real universe, the actual universe we live in, is not entirely smooth because it's full of various galactic clusters and a lot of long filaments of gas, as well as something that doesn't contain stuff, such as various regions referred to as voids. But in this case, the physicists studying this have always assumed that these individual clumps, on average, should not affect the overall expansion and should not have that much effect, especially if analyzing the entire universe as opposed to just one individual part. And that's essentially what this new research is trying to achieve. It's putting all of these assumptions to test, and actually a very rigorous test based on some of the most detailed data. And so here we have 3 separate studies, and specifically 4 researchers from Denmark and the UK, tested this FLRW framework without making the assumption that it was correct to begin with. And to do this, they relied on a machine learning technique referred to as symbolic regression. So basically, instead of telling a computer to feed the data to a specific formula, they let the computer search for mathematical expression that seems to best fit various observations of supernova and galactic surveys. So in essence, this is a model-independent approach and is quite unbiased because it starts from the beginning and tries to discover a formula. But what they found was a bit of a shock. Their analysis showed mild to even moderate deviations from the standard predictions in that 100-year-old cosmological model, with the results having a sigma of 2 to even 4, which in the world of physics potentially suggests some kind of a tentative discovery or something that is very intriguing. Normally in physics, it requires a sigma of 5 before something is confirmed. But in terms of mathematics, they looked at something referred to as Clarkson-Bassett-Lou test, which is a type of a mathematical consistency check, or essentially a check that tries to see if something is more or less correct or not. And well, if our universe follows these standard rules, the result of this test must be 0. But the data based on the Dark Energy Spectroscopic Instrument, or DESI, and the Pantheon Supernova Catalog, the 2 major catalogs we've discussed in some of the previous videos, and basically the largest observations of the universe to date, seem to suggest the result is not 0, and that the observations do not match predicted values. Now in this case, it's not certain why they don't match, because here it just tells us that something doesn't add up. The why part is still a mystery and is not tackled in any of these papers. But nevertheless, they do provide some possible resolutions and possible suggestions. Because assuming these violations are real, we still need to try to figure out what's causing them. And well, the first potential resolution is referred to as Dyer-Roeder effect. Yep, I know, lots of different terminology and lots of somewhat complicated stuff. But in a nutshell, when we look at distant supernova, the light doesn't travel through a perfectly average universe. It mostly travels through empty voids because matter is usually clumped into galaxies. And this, in theory, can bias our measurements, making the universe appear much emptier than it actually is. So in this case, there could be a bias based on supernova measurements, and it's something that needs to be addressed in some of the future studies. Alternatively, there is also something referred to as cosmological backreaction. This is the idea that the growth of those massive cosmic webs and these massive voids possibly changes the average expansion of the universe and makes the universe not so uniform after all. Or basically it creates local gravity effects that might create conditions where the universe accelerates a little bit faster and conditions where it accelerates a little bit slower. In other words, the universe might not be homogeneous and instead contains certain areas where things are just a little bit different. And well, until these recent studies, it was very difficult to distinguish some of these effects and explain why certain observations don't seem to add up. But because of these new studies, the overall results do suggest that it seems to be coming from the geometry of space itself and not some kind of a mysterious new particle or some form of energy that we never considered before. In other words, it's unlikely to be evolving dark energy particles or some strange fifth force in nature, but instead seems to be the result of geometry of space, which essentially means that cosmology and physics as a whole might actually go through a new renaissance and a new revolution. Because if this confirms that this FLRW framework is failing, It means that we now need to design new frameworks and create new, better models that explain everything. And that's the overall conclusion from these papers. Assuming that we don't find some kind of a different explanation, such as maybe some kind of a interacting dark matter particle or some bizarre new source of dark energy, the overall conclusion is that we might need to rework some of the models, and while the universe might not be as homogeneous or same everywhere as we initially thought. And importantly, once this solution is found, it's most likely going to solve a lot of modern issues, including the idea known as the Hubble tension you can learn about in a video in the description. And the best news in this case is the fact that we are going to be getting new data very soon, and over the next few years, even better measurements of the expansion rate are going to be released, which may either confirm this and suggest that we need to rework the models, or possibly explain everything in some other bizarre way. But essentially, just to summarize this video, as you might have learned, scientific truth in this case is not actually decided by the majority vote. And as of today, quite a lot of physicists are divided on a lot of different issues, with a lot of evidence pointing at different solutions. But these cracks in the modern standard model are not a failure of science. That's actually the important part. As a matter of fact, this is precisely why science works the way it does. Here, this is an invitation to find a much deeper, more accurate description of cosmos, and to essentially help us reassess our previous assumptions, and to then come up with a conclusion that makes a lot more sense. Which means that we'll definitely follow this up with additional videos once there is new data and new studies. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM directly, or by joining the channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.